Okay, let's talk about one of those incredibly powerful tools in SQL Server that, well, if you don't handle it with absolute care, it can really become your worst nightmare. We're diving into dynamic SQL today. Now, we all know the sheer flexibility it brings to the table, right? Building queries on the fly. Think about apps letting users build complex custom reports or those really adaptable search interfaces, or even, sophisticated scripts that have to work with databases where the schema might change slightly. Dynamic SQL really lets us push past the static limits of plain T-SQL. Makes our applications way more responsive, more versatile. It's like having this amazing linguistic toolkit you can programmatically shape to meet evolving needs right at runtime. But, and this is a really big but, one that, seasoned pros have definitely learned the hard way, this power is absolutely a double-edged sword. And today, we're honing in on what our source material calls a prevalent, frankly quite dangerous, anti-pattern. This happens when you use the execute command, or, its common shorthand, exec directly with string variables, especially where you're pulling in unchecked input from, say, the user, or even just from the application itself.
That's exactly right. What might seem like a quick, simple fix to a developer, well, it can unleash some devastating consequences down the line. This specific anti-pattern, it's not just about writing slightly inefficient code. Oh, no. It throws the doors wide open to two major, and often linked, problems that can seriously compromise both the security and the performance of your database environment. On the one hand, you've got that potentially catastrophic security risk SQL injection. We've all heard horror stories about that, attackers basically hijacking your queries to run their commands. And then on the other hand, there's the maybe less dramatic, but equally debilitating performance hit, SQL plan cache bloat. Both of these can absolutely lead to downtime, data loss, and, well, a whole heap of compliance and trust issues you really, really want to avoid.
Right. So consider our mission for this deep dive pretty clear then. We're going to unpack precisely how this execute anti-pattern actually works. We'll peel back the layers on the very real, often very expensive dangers it poses in the real world. And then, crucially, we'll zero in on the robust built-in solutions SQL Server itself provides to stop these issues dead in their tracks. Plus, we'll touch on a vital detection layer, sort of a crucial safety net, that can help you spot if these vulnerabilities might already be lurking in code bases you manage or support. So get ready. We're aiming to significantly boost how you secure and optimize your dynamic SQL. All right, let's start by really dissecting this execute anti-pattern at its core. The basic idea of dynamic SQL, like we said, is building a T-SQL query or command as a string, usually in a variable, and then just passing that string off to SQL Server's execution engine. The method that really embodies this anti-pattern, the one that sets the stage for major trouble, is using execute at SQL string, or the shorter XEC at SQL string. Let's make this more concrete. A common, really vulnerable example drawn straight from our source material. That product search scenario. Imagine you've got an application. User tucks a product name into a search box. Simple enough. A developer, maybe looking for the quickest way to filter, might think, okay, easy. Select products where the name matches the user's input. I'll just build a select statement as a string and plug the user's text right into the where clause. So in their TSQL code, maybe in a stored proc, they might declare a variable for the user input, let's call it at product name, and another one to build the SQL string itself, say at SQL. And then they do something basically like this: declare at product name in varchar 255. Now, obviously, in the real world, this value comes from user input. Set at product name mountain bike. Declare at SQL in varchar max. Here's the risky bit: building the query string by concatenating the input directly. Set at SQL and select producted product name price from production. Products where product name and plus at product name, plus the dangerous part, execute at SQL. Just pause there for a second and really look at that set at SQL line. They're literally taking whatever's inside the at product name variable and just jamming it through string concatenation right into the middle of the at SQL variable. That at SQL variable represents the command they want to execute. They're essentially stitching user-provided data directly into the code string that SQL Server is going to run.
And that, right there, that's precisely where the core vulnerability lies. As the source material really hammers home, the fundamental issue is unchecked concatenation in existing. The critical flaw when you use execute at SQL string this way, it's that SQL Server processes the entire content of that at SQL string variable as just one single batch of executable T-SQL commands. When you mix data directly into that string without any proper separation, there's absolutely no inherent mechanism for SQL Server to tell the difference. It can't distinguish between what you intended to be part of the command structure like select from where the column and table names, and what you intended to be treated purely as a data value like mountain bike. It all just arrives as one big, undifferentiated stream of characters that SQL Server tries its best to parse and execute. Yeah, think of it like giving someone instructions for a recipe mixed in with notes about the ingredients, all in one long sentence with no punctuation. If they don't know where the instructions stop and the ingredients start, they might, I don't know, try to cook the ingredient list itself. In SQL Server's case, if that ingredient list, the user input contains characters or keywords that happen to look like valid T-SQL syntax, well, SQL Server, by design, is going to attempt to interpret and execute them as part of the command batch. There's no reason not to.
And this leads us straight into the first and probably the most infamous consequence, SQL injection. Because SQL Server is just processing that whole string as if it's all code. If the user input contains not just data, but cleverly crafted code fragments designed to manipulate your query, the server will just blindly execute them, no questions asked. Let's go back to our vulnerable example and use that classic, really illustrative malicious input mentioned in the source, RR111. This isn't just random garbage. It's a meticulously crafted attack payload targeting exactly this concatenation weakness. Let's trace exactly what happens when that string, or R1 gets assigned to @productName and then concatenated into @SQL using that code snippet we just showed. Right before the execute @SQL call, the final string inside the @SQL variable would actually look like this. Select product name, price from production. Products where product name are 11111. Okay, now let's break down that resulting string from SQL Server's point of view, piece by painful piece, and see what the attacker actually achieved. 1. The developer's original query string started the where clause, like where product name greet. They intended to wrap the variable in quotes, but because they concatenated the variable inside the intended string literal, they often end up with something like product name plus plus. With our malicious product name, but concatenation becomes gone. Product name plus E plus $1 plus going. See that first single quote in the attacker's input. It pairs up with the preceding quote from the developer's code. That prematurely closes the string literal intended for product name. So the valid SQL after product name is now just empty string. 2. Immediately after that now closed empty string T, the attacker's input, or R11 gets appended. Or 11 is perfectly valid T-SQL. And T-tuple, that's a condition that is always true. By adding or R11, the attacker completely changes the logic of the where clause. It goes from find products where the name equals this specific string to find products where the name equals an empty string, which probably matches nothing. Or where 1 equals 1, which is always true. Because or 11 is always true, the entire where condition effectively becomes true for every single row in the production product table. Ouch. 3. Next up is the semicolon. In T-SQL, that's a command separator. We basically kill SQL Server. Okay, that command we were just processing, it's done now. Yeah. This is actually pretty crucial for the attacker. It lets them logically separate the query they just manipulated from any other valid code that might have followed in the original string. And 4. Finally, the double hyphen. That's the T-SQL syntax to start a single-line comment. Anything appearing on that line after the cancelled row is completely ignored by SQL Server. In the developer's original concatenated string, there might have been a closing single quote, or maybe other syntax fragments after where product name was inserted. The effectively comments out and neutralizes anything that was supposed to come after the attacker's injected code. This prevents syntax errors that could potentially stop their attack from working.
So yeah, what actually gets passed to execute isn't the intended select DAC where product name equals mountain bike at all. Instead, it's a query that the server interprets essentially as select product name, price from production. Products where RAB101, followed by commented out remnants, the original intent filter by product name completely subverted, gone. The database is effectively tricked into running an entirely different command. Give me all the rows from the table. This ability to inject and execute arbitrary code fragments just by blurring those lines between code and data, that is, as the source rightly points out, the fundamental flaw that SQL injection exploits. And why is SQL injection so feared? Well, it's a code injection technique, plain and simple. It specifically preys on poor input handling when that input is eventually going to end up in a database query. It works because the application isn't correctly distinguishing between what should be treated as trustworthy data and what could be executable code. Our source material actually outlines several types of SQL injection, which kind of helps illustrate just how broad the attack possibilities are. First, there's in-band SQL. This is where the attacker uses the same communication channel, usually the application itself, to both launch the attack and get the results back. The example we just walked through, where the attacker gets all the product data back directly. Classic in-band. Within in-band, you often see a couple of common tactics. Error-based SQL. Here, attackers deliberately craft input designed to make the database throw detailed error messages. Why? Because those error messages can inadvertently leak really valuable info stuff like database schema details, table names, column names, data types, maybe the SQL Server version, or even internal configuration settings. Attackers use this intel to plan more sophisticated attacks. Union-based spoofly. This is clever. If the application actually displays query results, attackers can inject union all clauses. This lets them combine the results of the original query, which they might have already bypassed with OR11, with the results of entirely separate malicious queries. Queries that pull data from other tables the application should never touch, maybe dumping usernames and passwords from a user's table, or grabbing customer PII or system configuration settings. Then there's inferential sequoia, sometimes called blind squoia. This gets used when the application doesn't directly show database results or error messages back to the user. It's trickier for the attacker. They still send malicious queries, but they have to infer the database's response or database purely on the application's behavior. For instance, they might inject a query that introduces a time delay only if a certain condition is true, like if select ASCII substring at password 1100, wait for delay 0.001 lay 055. Then they just time the application's response. Slow response, condition was true. Fast response, condition was false. Or they might inject true-false conditions into the where clause, like on or producted one in select count from users 10. If the condition is true, maybe the page loads normally. If false, maybe it errors out or looks slightly different. By sending tons of these queries, they can slowly, painstakingly infer the database structure and content, sometimes character by character. It's slow, yes, but very persistent. And finally, there's out-of-band sequoia. This is generally more advanced. It relies on the database server itself having the capability to make outbound network requests like DNS lookups or HTTP requests to a server controlled by the attacker. The attacker injects code that basically tells SQL Server, hey, try to connect to this specific URL or do a DNS lookup for this attacker-controlled domain. For example, using xpetertreeattacker.com share or maybe clever tricks with 4XML path, the attacker just sits there monitoring their own server logs. If they see the connection attempt or the DNS lookup hit their server, they know their injected code executed. They can even potentially exfiltrate data by encoding it into those DNS requests or URLs. This completely bypasses the normal application communication channel, the consequences if any of these succeed. Well, the source uses the term potentially catastrophic, and honestly, that's not hyperbole. These aren't just abstract risks. They are real, devastating impacts that have crippled companies.
Don't miss out. Smash that like button, subscribe, and explore our other videos in the playlists.